In lecture 17, mainly we will discuss the inverse system by using Laplace transform, and also we will discuss the properties of inverse system like causal, stable, and minimum phase. Okay. So first we will discuss inverse system concept. Okay. For a given system, if the impulse response is h of t, okay, we are considering a LTI system. So this is a LTI system which obey linearity property and time invariant property, and x of t is the input and y of t is the output, and the impulse response of the system is represented by h of t. So the system response is h of t, and the impulse response of the inverse system, if there is an inverse system exists, that is h inverse of t. Okay, so it should satisfy the condition that h inverse of t convolution h of t will give you del of t. Okay, that is there is a system, the output of the system is first system. For example, this is the first system. Okay, and now I will consider another system. Okay, this is again an LTI system, and if you apply y of t as the input of the second system, and if you are getting x of t as the output, okay, then this system response is simply h inverse of t. That's the meaning. Okay, if you apply an input to the first system, you will get an output y of t, and if you apply the y of t as the input of the second system, you will get the input x of t. Okay, then we can call it as there is an inverse system exists. So that inverse system is represented by h inverse of t. Okay, then it should satisfy the condition in time domain. We can say that h inverse of t convolution h of t is del of t. Okay, that's an impulse signal. If you take the Laplace transform of this particular equation, you will get the transform of h of t. Laplace transform of h of t is h of s, and the Laplace transform of inverse system is represented as h inverse of s. Then the convolution operation becomes multiplication in Laplace transform domain, and the Laplace transform of del of t is 1. So we can write this. So the h inverse of a system you can calculate by 1 by h of s. If you take the reciprocal of h of s, you will get h inverse of s. Okay, another point you can see that if you take the inverse, zeros of the inverse system, okay, zeros of the inverse system, so inverse system is h inverses of, are the poles of h of s. For example, if h of s is equal to s plus 1 by s plus 2, okay, this is the system, assume that this is a system, then h inverse of s will be s plus 2 by s plus 1. So from this you can see that zeros of the inverse system, zeros of the inverse system means s plus 2. Okay, this is 0 of the inverse system, is actually the pole of h of s. Similarly, you can say that the poles of inverse system, that the poles of the inverse system is actually the zeros of the zeros of the h inverse of s. So that's the meaning, zeros of h of s. Okay, now we'll discuss the properties of this particular system. So first we will discuss what's the condition for a stable and a causal inverse system exists. Okay, we need to verify that whether there is a stable causal inverse system exists. So we need to verify this. If an inverse system exists and that inverse system is stable and causal, means we need to verify this condition with respect to h of s. Okay, assume that there is only h of s. With respect to h of s, we can say that is there any inverse system exists, and whether that particular system is stable and causal. So for that, zeros of h of s. Okay, so make it clear, in order to find whether there is an inverse system, a causal and stable inverse system exists, we want to check this particular condition. For that, we will take h of s and we'll take the zeros of h of s, and if the poles, sorry, all zeros of h of s, okay, zeros of h of s lies left half of s plane, then we can say that the inverse system exists and the inverse system will be a causal and stable condition. Okay, we already discussed in the previous lecture to check the causality and stability. Okay, this is the sigma axis, this is the j omega axis. For example, in order to check a system is causal or stable, actually we will monitor the poles, but if a system is causal and stable means it should include j omega axis and all the poles should be on the left half of the s plane. So that's a condition, but in this case we are verifying whether the inverse system is stable and causal. Okay, whether the inverse system is stable and causal, that's why we are going for a poles, because this poles becomes zeros of the h inverse of s. So this is about h of s. Okay, that's why we are verifying the zeros, and a system is said to be minimum phase. Okay, h of s has all of its poles and zeros in the left half of this plane. If all the poles and the zeros, so in order to make a system is causal and stable, either if you are considering h inverse of s, we will verify the poles. Okay, but with respect to h of s, we want to know about h inverses, we will take zeros. So that's the meaning. Okay, and now we need to verify a system is a minimum phase or not. So h of s, all of its poles and zeros in the left half of s plane, then the inverse system is minimum phase, or the system is minimum phase. And non-minimum phase, so such system cannot have a stable and causal system, because non-minimum means some of the zeros will be on the right half of this plane. That's the meaning. System is minimum phase means all the poles and zeros lies in the, so poles and zeros lies in the left half of the s plane. Okay, and non-minimum phase means some of the zeros in the right side. So if we take the inverse, this becomes poles, and there will be a pole in the right hand of this plane. This is h of s and this is h inverse of s. Okay, here it will be, okay, sorry. So that's why 0 in the right half of s plane. So that's why cannot have a stable and causal inverse system if a non-minimum phase. Okay, now we'll do one problem related to this. So we need to verify in this particular question, consider a system described by the differential equation and find the transfer function of the inverse system. So we need to find the transfer function of the inverse system, and we need to verify that it is a stable and a causal system exists. Okay, in two ways we can approach this particular problem. We can find h of s, and with respect to h of s we can say whether this system is stable or not. So at that time we will take zeros. Or if you are finding h inverse of s and if you are verifying whether the system is causal or stable, at that time we will take poles. Okay, we will discuss that. First we need to write the transfer function of this Laplace transform of this particular equation. So if you take the Laplace transform of this particular equation, it becomes y of s, s into y of s plus 2 into y of s, okay, is equal to s square into x of s plus 2 into s x of s minus 3x of s, and you can take y of s here and x of s common here, and if you rearrange you can write y of s by x of s. Okay, then it becomes s square plus 2s minus 3 divided by s plus 2, and which is equal to h of s, because this is the transfer function. And now we got the transfer function of the system. So inverse transfer function of the inverse system can be calculated 1 by h of s. So we'll take the inverse, so s plus 2 divided by s square plus 2s minus 3. So if you factorize this, you will get s plus 2 divided by s minus 1 into s plus 3. Okay, and now we can check the poles and zeros. This is sigma and this is the j omega axis. Okay, this is j omega axis. You can see that poles of or this is the pole zero plot of inverse system. Okay, inverse system. So we'll take s is equal to 1 is 1 pole, and s is equal to minus 3, and s is equal to 2 minus 2, there is a 0. Okay, there is a minus 2, and you can see that one pole at s is equal to 1 means it's the right side of the right half of the spline. Means if a system should be causal and stable, it's all of its poles should lie to the left half of the spline. So we cannot say that system is both causal and stable. So that's a conclusion. System cannot be causal and stable. Okay, both causal and stable, to be both causal and stable. Why? Because one pole of this particular system lies at right half of the S-plane. In order to make a system is both causal and stable, all the poles of the system should be on left half of the S-plane. Okay, this is the condition. So here S is equal to 1 means right half of the S-plane. Okay, that's why there is no such stable and causal system, inverse system exists. The same thing we can evaluate without calculating the inverse also. Okay, we can calculate or we can verify this with respect to h of s also. If you are verifying with respect to h of s, that is there any inverse system with causal and stable exists, at that time we will verify the 0. Okay, but if you are directly taking the inverse, then with respect to poles we can talk. Thank you.